Um, a very good evening to all. This is live discussion session number 9 for the course entitled Basic Thermodynamics, Classical and Statistical Approaches. And the course code is NOC 24CY04. And myself, Akash Gutal, I'm PhD student of the Department of Chemistry, Indian Institute of Technology, Jodhpur. So today uh, is the live discussion session number 9. And we are going to first revise certain things from the last week NPTEL lectures. So what we have seen in the uh, last week's lectures is we have started classical. Uh, we have started the statistical thermodynamics part, in which we have completed the basics first. In last week, we have completed the basics, and this week we have moved towards the basic fundamentals of classical thermodynamics, which related to the partition function and all stuff. So we have started from what are the classical particles, the types of particles, where we have discussed the types of particles, where the general classical particles. So, so the classical particles are distinguishable, distinguishable particles. And what we have seen is the bosons are quantum particles, and they are indistinguishable. And we also known that they have integer spin. So their spin can be 1 or 2, 3, but not half or something. So their only integer spins are allowed to bosonic particles. And third particle type is the fermions. And fermions are indistinguishable and have one half spin, or spin with integer multiple of half. And we know that the example of boson is photon. So bosons can be photon, which is having integer spin. The example of fermions we can give as one example as electron. And classical particles, as we know, they are distinguishable, and uh, we can consider any distinguishable particle as a classical. Then we have calculated so the distribution for boson, fermions, and classical particles. So how can we get the microstates for bosons, or we can say the distribution for the boson is, so we have, so number of bosons in ith level divided by total number of bosons. This can be given as 1 by a into b raised to epsilon I minus 1. Right? This we have derived in the class. Similarly, for in case of fermions, so these are indistinguishable. Mm. Similarly, for fermions, n I by n is will be a into e raised to b epsilon I plus 1. Right? And these are also indistinguishable. But so speciality of fermions are they follow Pauli's principle. So what Pauli's principle says us is that no two fermions can have the same uh, quantum numbers. Because of that, uh, at same energy level, only two fermions can be uh, can can get that position, and they will be having opposite spins. Okay, so remember they follow Pauli's exclusion principle. And the third one for classical particle, we know the Maxwell-Boltzmann distribution is valid for classical particle. So we'll write in summary, we got three distributions. This each distribution for boson fermions, different scientist names are given. So we will summarize these three distributions. First one is Maxwell-Boltzmann distribution. This generally for classical distinguishable particles, which is Nj divided by N is equal to 1 upon A into e raised to epsilon I b. So kbt. So here we have b is equal to 1 by Boltzmann constant into temperature. Then second distribution is Bose-Einstein distribution, which is for generally for bosons, which have just we have written 1 upon A into e raised to epsilon I divided by kbt plus 1. And similarly, third thing is Fermi derived distribution. So the Fermi derived distribution is for fermions, A into e raised to epsilon I by kbt minus 1. Right? So these are important distributions that we are going to use today's to solve today's problem. Then we uh, we introduce what is the value of A. Okay, we find out what is the we found out the what is the value of A here. So A is turned out to be the thing called 1 by partition function. Okay, and this so we got AI. Let's say for Maxwell-Boltzmann distribution, we got it as A into e raised to minus beta epsilon I, where beta is equal to 1 by kbt. But we found that A is nothing but A is nothing but 1. Here A is at the uh, at, at at the denominator. So to write it properly, so here A we defined A 1 by uh, should be summation of e raised to minus beta epsilon, right? And this part is q, which is nothing but partition function summation of epsilon beta epsilon beta by sorry beta into epsilon. So this is the partition function. So you will be having here. So our equation will become e raised to minus beta epsilon I divided by um, summation of e raised to minus beta epsilon I. So this basic equation we have derived. Okay. So Q here Q is called the partition function. Okay. Then we move towards the Boltzmann's distribution. Boltzmann distribution where we denote it as Pi is equal to the number of particles at ith level divided by total number of particles is nothing but can be given as e raised to minus epsilon I by kbt divided by sorry for that kbt divided by summation of e raised to minus epsilon I by kbt for all the summations, and we have defined that e raised to minus epsilon I by kbt, and the quantity at the denominator we have defined as q, which is nothing but q is the partition function summation of e raised to minus epsilon I by q. And we defined entropy similar way. What is the equation for entropy? Reduces to minus kb into summation of ipi lnpi. So this is given as equation for entropy. And there is another entropy called in the information theory, which is called Shannon entropy. So that entropy can be defined as S is equal to so there will not be kbt here. Okay, in Shannon entropy in information theory there will not be kb. Okay? So this is called as Shannon's entropy. This is generally used in information theory. We'll solve some one problem regarding this Shannon entropy, which is actually related to the distribution of the particles. So, and after that, at the end, we have uh, uh, derived some link between the classical thermodynamic quantities and the statistical thermodynamic quantities, where we have defined. Let me add one new slide. So we have defined what is the thermodynamic energy in terms of that is internal energy in terms of uh, the statistical thermodynamics is nothing but the average energy, and we can get that average energy by uh, summing all the energies of the each and individual level into energy of each individual level into their pi values, that is Boltzmann distribution values. The summation gives us the average energy, which we call it as internal energy in our classical thermodynamics. Similarly, observable pressure, the classical thermodynamics can be given as summation of p small pi into capital Pi, which is nothing but average pressure, and similarly the observable volume V, it's the average volume, the summation of Vi into the same capital Vi. And which is, we have seen that this is the same as the analogy of uh, in quantum mechanics. In the wave function analogy uh, we have seen in the lectures. So in statistical thermodynamics, whatever the quantity, the average value will be always, suppose in case of energy, the average value can be calculated as summing or integrating over the probabilities of energy E into the energy of that level over into the del E. Okay. So this is the statistical definition of averaging. Statistical definition of energy, or the respective quantity, whatever the same quantity in the classical thermodynamics. And last one, we have derived translational partition function. I will directly write its equation for translational partition function, which can be given as 2 pi mkbt by h square raised to 1 half into L, and this is for only one dimension, and we have derived that the average value in one dimensional of in an average value of energy in one dimensional is 1/2 kBT. Similarly, for three dimensions, it will be average value can be given as 3/2 kBT because we have 3 degrees of freedom. The average value turns out to be 3/2 kBT. The same as that we seen in the kinetic theory of gases. Fine. We will start doing our problems for today's session. So the question number one is, which of the following distributions corresponds to Bose-Einstein statistics? Uh, AI is the average number of particles occupying energy level epsilon I, and omega I, Wi is the degeneracy of ith level. So we have asked that which of the following distribution correspond to the Bose-Einstein statistics. So please uh, do the analysis and tell me the answer. So here only thing is different is the Wi, which is we called as degeneracy. So where the degeneracy we can put, where is the question. So we know what is the Bose-Einstein statistics, but we have not considered the degeneracy while deriving the equation. So this question is asking, we are having degeneracy for each level, which is denoted by omega I, and we need to uh, incorporate it with the distribution. Take 2-3 minutes to solve this problem. So what this question suggests is we are having system where where each level having some degeneracy. Okay. Different level have their different degeneracies. And we are asked to these particles are occupied in it. Fine. So what is asked is we know that for Bose-Einstein distribution, For non-degenerate system, only if there is no degeneracy for any level, we have the distribution 1 upon exponential of alpha plus beta epsilon I minus 1. But if the degeneracy is there, uh, this AI is nothing but Ni by N. So this is actually fraction. And fraction, if we allow more number of energy levels for the same energy, then its fraction will actually changes in multiples of number of levels that we are keeping as a degenerate. So it will be multiplied by number of degeneracy of that level. Okay, so our equation will reduce us to omega I or wi divided by exponential alpha plus beta epsilon I minus 1. So this must be the equation which is answer as option number 3. So the next question is, what is the temperature of two level system of energy separation equal to 5.74 into 10 raised to minus 21 joule when the population of the upper state is one fourth of that of the lower state. So we try to solve this problem. Take 2-3 minutes to solve. It's again related to the distribution. Uh, Ni by n. Ni by n is the same system. So first we will separate out the given things. So we have only two level system. So this is N0 and this is N1. And the population of upper state is one fourth of that of the lower state. Upper state have population 1 by 4 that of lower state. This is the condition given. So from here we can find out what is the N1 by N0, which is nothing but 1 by 4. We have equation for ith level is the distribution or the fraction of particles where n is the total number of particles, and this is a two level system, hence we will be having e raised to epsilon I by kBt divided by summation of e raised to epsilon I by kBt. And what so we will write this equation for individual energy level. When we write it, suppose n1 n1 will be having the same equation e raised to minus epsilon I by kBt. Suppose we are write this equation for n1 divided by summation of e raised to minus epsilon I by kBt, and for and we let their energy will be epsilon 1 and epsilon naught. So n naught by n will be e raised to minus epsilon naught kBt, and the summation of I running from here, I running from 0 to 1, and here I running from 0 to 1, e raised to minus epsilon I by kB. And we have these two equations. If we divide the equation 1 by 2, what we will have? N1 by n naught, which is e raised to minus E1 by kBt divided by e raised to minus epsilon naught by kBt. Right? And if you do it, then this will reduce to e raised to minus, or we can say E naught minus E1 by kBt. Look, this is N1 by N naught. So what is given N1 by N naught is 1 by 4. So we put it, we will get this 1 by 4, and the separation is given 5.74. And we know that epsilon naught is greater in energy. We considered epsilon 1 is higher in energy, which means minus of that will reduce it to e raised to minus of 5.74 into 10 raised to minus 21 divided by kb into t. So if we solve this, we can do we can write 4 is equal to e raised to as a positive 5.74 into 10 raised to minus 21 by kBt, and we know the kb value. Kb is equal to 1.38 into 10 raised to minus 23 joule per Kelvin. Fine. And this is, if you do it, to calculate it, let me add one new slide. Fine. So what will be having? 4 is equal to e raised to 5.74, 10 raised to minus 21, divided by 1.38 into 10 raised to minus 23, and the temperature that they have given is we need to calculate. Sorry, temperature we need to calculate. And if you take natural log of both the side, that will reduce 5.74 into 10 raised to 1, 1.38 3 dot t. So t will be left side. Log of that will give you answer as, if you calculate it, that will give you 300 Kelvin. And answer should be option number 3, 300 Kelvin. So the question number three is find the incorrect statement about Maxwell-Boltzmann distribution. So the four statements are given. At all temperatures, pure particles are at higher energy than at lower energy. At very low temperatures, essentially all particles are at the lowest possible energy. As the temperature increases, more and more levels become populated. None of them. So please think about it and try to find out the answer. Take your own time, 2-3 minutes. So find the incorrect statement about Maxwell-Boltzmann distribution. So it's given that at first statement we read all temperatures, fewer particles are at higher energy than at lower energy. So if you consider the Maxwell-Boltzmann distribution, Ni by N is e raised to minus epsilon I by Q divided by Q. So if we see this uh, Maxwell-Boltzmann distribution, Q will not be changed. It depends upon the number of energy levels and the energies. But what will change is the epsilon I. The higher the energy level, epsilon I will be higher. And if the I will high, this e raised to minus epsilon I divided by kBT will be less. So this Ni by N factor will be less for the higher energy levels, which means you will be having a distribution. Suppose this line represent the number of Ni by N fraction, which will be, which we can say, suppose this is the graph of energy. So you will be having N. So your distribution will be the number of particles at, so consider it as N I by N, right? Or simply we can consider it as number of N particles. Fraction you can consider, but number of particles at I. So this will more at lower energy and will be reduced, will be uh, reduced exponentially as we increase uh, the energy level and we go the higher and higher energy level. But if we see this equation is actually having temperature. If you are having temperature, if it tends to infinity, then what is the final point of this distribution will be, final point of this distribution will be all energies are equally occupied. So this will be the case and T is at infinity. So what the first statement tells us is that at all temperatures, fewer particle at higher energy than at lower energy. So this statement is true. Why? Because at even if you go at temperature at infinite temperature, the possibility will of the distribution of the particle will be equal for all energy levels. So that will never be that case will be never will be there where you are having more number of particles at the higher level and lesser number of particles at the lower level. In case of Boltzmann distribution, you must consider it's valid for only Maxwell Boltzmann distribution. That's the uh, thing related to the Boltzmann version. So what we are having is at this statement is actually true. So this is true statement. It's always there because all the temperatures, even if you go for the infinity, these particles are distributed. When you go for t raised to infinity, the all energy levels are equally filled. Means the equal probability for all energy levels. So at very low temperatures, essentially all particles are at the lowest possible energy. So at low temperature, essentially our particles are the lowest possible energy. When you lower this temperature, then the particles at the higher energy level will fall down eventually at the lower energy level, and this will increase the population of the lower energy levels. So that the second statement is also true. Third statement is as the temperature increases, more and more levels become populated. So yes, that statement also true. Temperature once we increase, this will the distribution shift towards the higher energy level. But please consider that at T tends to infinity, all energy levels are filled equally. So that is the final point. But what the third statement is telling you that as temperature increases, more and more energy levels become populated. That's the true statement. So what we have asked is find the incorrect statement. So all three statements are true. So answer should be none of the above. Option number four. So the question number four is here. In a system with energy levels evenly spaced by 1.5 into 10 to the minus 19 joule at 500 Kelvin, N naught is given is 1 into 10 raised to 10. What is the N1? Same type of question that we have solved. Please try to solve it. Take 2-3 minutes to solve this question. So here the energy levels are spaced by 1.5 into 10 raised to minus 19 joule, and the temperature is given as 500 Kelvin, and population at N naught level is 1 cross 10 raised to 10, and N1 level we need to find out. So the same uh, equation that we have derived previously, we are going to use the same equation. N1 by N naught is equal to e raised to minus E1 by kBT divided by e raised to minus epsilon naught by kBT, which will give you N1 by N naught is equal to e raised to E naught minus epsilon 1 by kBT. So we know N naught is equal to 1 into 10 raised to 10. So N1 is 1 cross 10 raised to 10, and epsilon naught minus epsilon 1 is nothing but, as the N1 is higher energy level, this will be minus 1.5 into 10 raised to minus 19 divided by kBT. If you check this from 10 raised to 10, if you reverse it, or that's fine. Okay, we can directly calculate it. So N1 is equal to e raised to minus 1.5 into 10 raised to minus 19 divided by kBT into 10 raised to 10. This will be e raised to 1.5 into 10 raised to 15 by 1.38 into 10 raised to minus 23 into, what is the temperature? It's 500 to 10 raised to, if we solve this, is 1.5 divided by, do the calculation, plus 1.5 divided by 1.38 divided by 5, if you do, it is to minus 0.2173 into 10 raised to minus 19 divided by 10 raised to minus 23 into 10 raised to 2. Okay, and into 10 raised to 10. This is in an exponential. Okay, let me add one more slide. So, which is, and what we are getting is, so 10 raised to minus 19, and this is 10 raised to minus 23 in cross 10 raised to 2 will be 10 raised to minus 21. If you, it goes in the upside where 10 raised to 21 and 10 raised to 2 will remain. So this will be minus 21.73. So we are having N1 is equal to e raised to minus 21.73, and this to 10. Should we calculate this? It's turned out to be 3.6541 to 10 raised to minus 10 into 10 raised to 10. So N1 will move raised to, so 10 raised to 10, this will cancel out, and then 3.6541, which the options are given, which is near to, if you convert it into integer, that would be near to 4. Answer should be Option number A4. Right. The next question. Calculate the entropy for the following distribution. There is one correction. Entropy, this should be positive, okay? Entropy can't be negative. So, so we need to calculate the entropy of the following distribution. Distribution is given. We need to calculate the entropy. And the hint for this question is this is related to Shannon entropy, which is entropy generally used in information. Please try to calculate. So we left this one option as negative one. That's it. So this is in this question, the distribution is given, which is the probability distribution, and the I is 0, 1, 2, 3, 4. If you sum up this entire distributions, you will get 1. And we know uh, we have the equation for entropy, which is called Shannon entropy. Is S is equal to minus pi of individual partition probability into ln pi summation over all. Let me write it properly. Negative of summation of pi ln pi. So why I say it should not be negative? Because probability pi is always less than 1. Because it is less than 1, if you take logarithm of the value which is less than 1, which is will be the negative value. And this negative summation of all negative values and this negative in the equation will cancel out, and we will having the positive entropy value. So this equation itself suggests that the entropy cannot be negative. So if you put things in the equation, this will be P1 ln P1 plus P2 ln P2 plus P3. I just stop 0. Okay. Right. P not not 1 P2 P3 ln P3 plus P4 ln P4 plus which is, yeah. So this is the total entropy we will be getting. So what is the value? 0 ln 0, which is plus P1 is zero point 0.1 ln zero point 0.1 plus zero point 0.2 ln zero point 0.2 plus zero point 0.3 ln zero point 0.3 plus zero point 0.4 ln point. So this will be 0 because anything multiplied by 0 will be 0. We will be having the Shannon entropy as, if you calculate this thing to do the logarithms and add them, we'll get minus 1.28 S. So S is equal to 1 point. Your entropy will be option number A, 1.28. So the question number 6 is find the correct statement. First statement is bosons are indistinguishable quantum particles. Fermions have integer spin and follow the Fermi statistics. Bosons follow the Boltzmann statistics and can reside in same energy levels. Fermions are indistinguishable and not more than two can stay in the same energy level. So let's try to find out the answer. Take 2-3 minutes. So bosons, the first statement is bosons are distinguishable quantum particles, which is uh, wrong statement because they are indistinguishable quantum particles. This is wrong. Fermions have integer spin and follow the Fermi statistics. We know that fermions, that electron, positron, uh, these fermions will have half integer spins. So this second statement also wrong. First also wrong. Third is bosons follow Boltzmann statistics and can reside in same energy levels. This is true that they can reside in the same energy levels, but they don't follow the Boltzmann statistics. Boltzmann statistics is followed by the distinguishable particles, and boson will follow Bose-Einstein statistics. Okay, that is wrong. Fermions are indistinguishable, and not more than two can stay in the same energy level. It's true that fermions are indistinguishable, and not more than two can stay in the same energy level. It's also true because at the same energy level, they will be having opposite spins, one half and minus half. And they can stay in same energy level, only two in number. So this is correct statement. The option number four. Answer should be option number four. Next question is the ratio Nj by Ni is equal to 0.20 for a system at 175 Kelvin. What is delta epsilon ij for the system? Please calculate. Take 2-3 minutes and tell me the answer if you got, if possible. So we have Nj by Ni is 0.20 and the system at temperature is 175 Kelvin and delta epsilon ij we need to calculate for the system. So we know the same formula is useful here. Ni by Nj by Ni is equal to e raised to minus epsilon j by kBt e raised to minus epsilon I by kBt, which will always give you e raised to epsilon I minus epsilon j by kb. And we need to find out this ei minus ej. Uh, so I to j. Okay. So if you do the same thing, it's 0.20. Okay. Uh, so let's say it's epsilon ij by kbt. If you take a log at the both the sides, and then 2, then 0.2 is equal to then epsilon ij t. So j is equal to kbt, and then 0 point, which is nothing but 1.38 into 10 to minus 23 into 175 into 0 point, sorry, ln 0 point, natural log of 0.2, which is, if you calculate it, then you will find the value is 3.8867 into 10 raised to minus 21 epsilon ij. Right? And the closest option is uh, minus 21, 3.88. It's option number A. Next question. For a four particle system with six quanta of energy in the following distribution, what is the number of microstates for bosons, fermions, and classical particles? Please try to find out the answer. Take 2-3 minutes to solve. So for a four particle system of six quanta of energy, in the following distribution, what is the number of microstates for bosons, fermions, and classical particles? The distribution is given, and first we consider for bosons. What are the possible distribution? So if you consider the bosons, bosons are indistinguishable particles, and they can occupy uh, same energy level. Uh, with many number of bosons can occupy the same energy level. And because they are indistinguishable for the fixed energy, their number of microstates for the given distribution will be should be one, because even if you interchange the particles at the fourth energy level or 4 epsilon level and 1 epsilon level, suppose even if you interchange them, because they are indistinguishable, then there will not be change in the microstate. So only one possible microstate can be uh, can we can depict, and because of that, bosons will be having only one microstate for the given system. In case of fermions, the fermions are also indistinguishable, but they can occupy or only two fermions can occupy the same energy level. Here the condition is fulfilled, and because of indistinguishability, the fermions will also have number of microstates 1. But if you consider the classical particles, for the classical particles, we know that they are distinguishable. And once if they are distinguishable, then what are the arrangements we need to calculate? For the 4 epsilon energy level, the number of arrangement, the or let's start from the bottom. From the bottom, for 0 epsilon, the possibility of this particle, if all particles are distinguishable, we are considering it, the possibility of the one particle being at the energy level 0 epsilon is number of total number of particles are 4 and 1. Similarly, in the next level 1 epsilon, this will be uh, 3 and 2 combination. Sorry, it should be C. So the combination 4C1 and the combination of 3C2 after that, and this is the combination problem. At the end, we'll be having only one particle left. We need to distribute in the only one uh, energy level. That's a 1C1. And the total number of combinations are nothing but their multiplication 4C1 cross 3C2 cross 1C1 combinations. So the combination will be 4 factorial divided by 3 factorial into 1 factorial cross 3 factorial divided by 2 factorial into 1 factorial, and this will be 1 factorial divided by 1 factorial into 0 factorial, which is nothing but the 1. 4 factorial cross 3 factorial by 3 factorial 1 factorial cross 3 factorial divided by 2 factorial, uh, 3 cross 2 factorial into 1 factorial into 1. So this will be cancelled. We will be having 4 cross 3 cross 1, which is nothing but 12. And answer will be option number first. So the last question, the next question is the following is the distribution of 5 particle system with 5 quanta of energy. Find the correct statement given below. So the quanta and particles, the distribution is given, and 4 options are given. So please try to find out the answer. So two distributions are given, and we are given some conditions, and we need to find out what is the uh, correct statement. We should not call it as conditions, but we can call it as just their statements to find out the correct statement given to you. Please try to make a guess. To solve this problem, you should know what are the boson, fermions, and what are their properties, as we discussed previous example and the division section. They take 2-3 minutes to solve. So the first statement is distribution A and B holds true for bosons, fermions, and classical particles. So A and B, if you see in A, we have three particles in ground state, and in B, we have two particles in the ground state, which is true for the boson, it's right. But in case of fermions, it is not true because single energy level must be filled with two particles or two fermions. But that is not the case in the first A distribution. So that's why the first answer will be first statement will be wrong statement. Second statement is the distribution A holds true for classical particles and distribution B is true for bosons and fermions. So the second statement is uh, if you see the distribution A is true is for classical particles. Why? It's true because the classical particles can occupy any of the energy level, any number, and the distribution B, if you see, is true for bosons and fermions. So, so this let hold for this statement. The next statement is distribution A holds true for bosons and fermions, and distribution B is true for bosons, fermions, and classical particles. So, uh, so if you see the distribution A holds true for bosons and fermions is wrong because fermions can't have more than two particles in one level. So third option is also wrong. So we need to check for second and fourth. The fourth is distribution A holds true for bosons and classical particles, and distribution B holds for boson, fermions, and classical particles. If you see for the statement P and D, or we can say the statement second statement and the fourth statement, If you compare these two statements, the most appropriate statement will be the fourth statement because the distribution of A hold true for bosons and classical particles. This both can be explained by first distribution, and distribution of B holds for bosons, fermions, and classical particles. Even though this second statement is true, but it is not giving you the complete picture or the complete possibilities of the given situation. But the fourth statement, if you see, it gives you the complete information, and that's why we choose the correct statement as the fourth statement. So, and because the second statement is incomplete, though it is true, but it's incomplete. Because of that, the answer should be fourth. Last question. Given a two-state system in which the low energy level is 600 calorie per mole and the high energy level is 1800 calories per mole, and the temperature of the system is 300 Kelvin. What is the average energy? E. So we need to find out the average energy. Four options are given. Please try to calculate it. Take 2-3 minutes. So if you see in this question, the two-state system is given, but the low energy level is at 600 calorie per mole, and the higher energy level is 1800 calorie per mole. For simplicity, we can convert them into joule per mole. Let's convert them into joule per mole. The conversion factor we know that 4.18 need to multiply. This will give you 1.800 into 4.18, which is nothing but if you do it, then 1.800 cross 4.18, which is 7524 joule per mole. Similarly, for 600 into 4.18 joule, which is 604.182508 joule per mole. If you see, uh, the and the temperature is given as 300 Kelvin. And we need to find out what is the average inertia. So from previous discussion, we know that the average inertia formula is it's a summation of individual EI into the Boltzmann distribution of EI or and we know the PEI is e raised to minus EI divided by KBT divided by the partition function Q. Okay. First, we need to calculate what is the partition function. And we know from the formula that the partition function is summation of sorry e raised to minus EI by KBT, which is nothing but e raised to minus 2508. And as we are having here the per mole, okay, we are having things as a per mole, then we can write it. First, I will convert this equation into. We can write the Boltzmann distribution in terms of uh, for per mole values. So this Kb will convert into R into T, RT, and the formula for Q will be e raised to minus EI by RT summation, which is e raised to minus 52508 divided by 8.314 into temperature is 300 Kelvin plus e raised to minus 7524 divided by 8.314 300 Kelvin. If you do it, calculate it, first value will come out to be 0.3658 plus 0.04896. Okay, and the partition function value will turn out to be 0.4148. If you add these two numbers, get the partition function as Q is equal to 0.4148. Okay, and substitute in this equation and calculate the what is the average energy. Let me add one new slide. So what is the average energy? Like average energy will be summation of P into PEI. So we have already calculated the individual distribution of EI. Okay. So you only need to multiply it 2508, or we can say we have converted these things into joule because of our simplicity we need to use R is equal to what 8.314. But once we final answer, we need calorie per mole. So EI we will put as unit because this is the unitless number. We can put EI as 600 in calorie per 600 calorie per mole into PEI that we have calculated is 0.3658 plus 1800 into 0.04896 divided by the partition function. So the partition function is 0.4148. If you calculate this, calculate this, then turn out to be 52, it's 741.581, right? Which is close to the options given is 743.7443 calorie per milliliters. And the option number is option number first should be the answer. So this completes our today's session. And if you have any problems or if you have any doubts, you can ask. I will be here for 10 minutes. Only 10 minutes are left. If you have any problems, you can ask. Thank you very much for attending the session. We will meet next week, Tuesday, 7 to 9 p.m.